Hello, everyone, and welcome back. So we're talking about exponential and logarithmic functions, and specifically in this video, we want to talk about graphing logarithmic functions. So how do we go about graphing logarithmic functions? Well, we first want to talk about a few things together. We want to explore this base, all right? So we want to explore the value of the base and how it affects the graph, okay? So we have over here y is equal to log bx, and we want to explore how does changing the value of the base affect our graph. So let's have a look at this function over here. They've given us this logarithmic function, all right, going through, oh wow, that was really bad. Okay. All right, let's try and sketch this as best as we can. So this is log base 3 of x, okay? So this one is this function over here, y is equal to log base 3 of x. And they're telling us that, they're saying, okay, well, you have this base that is 3, and we know that at 1 and 0, we have this intersection. We also know that if x is equal to 3, then y is equal to 1. Why is that? Is because remember, if I have log base a of a, this is always going to equal to 1. So if I have log base 3 of 3, well, that's going to equal to 1 too, right? So when x is equal to 3, we get y is equal to 1. So this point is 3 and 1. This point is 1 and 0. Okay, so we've just identified a few points here, and I want us to explore a few things here. We want to look at a few functions in order to determine kind of like what happens if I change this base to something else, if I reciprocate the base, and so on. So let's explore how y is equal to log base 10 of x would look like, okay? So what point it would intersect this, and then we also want to look at, let's do it in a different color, y is equal to log base 1 over 3, okay, x, and then we want to look at y is equal to log base 1 over 10 x, okay? All right, and then once we do this, we want to kind of understand, okay, so how does this affect our graph, right? So let's go and do this on our graphic calculator over here. Okay, so this was an old one. Let's create our new ones. So over here we have log base 3, so that's one of them. Log base 3. And then we could put over here log base 1 over 3. And then of x, we could do another one over here. Log base 10 of x. And one last one, log base 1 over 10 of x. So we want to understand basically what's happening when I have a fractional or a reciprocated base. So we have 1 over 10 over here versus having a base of 10. All right. And then let's graph this together. So once I graph this, it looks like this. And I want us to remember which, and just give me a sec here, because you need to always select it if yours has that option. So have a look at this. Obviously, they're all intersecting at 1 and 0 because we know that log of 1 is always going to be 0. And so the difference here is that when I have log of 1 over 3 and log of 1 over 10, let's move this actually right beside each other. Let's see if they'd let us. They're not letting us. That's okay. So over here, look at the ones that are reciprocated. 1 over 3 is the red one, and 1 over 10 is the purple one. Have a look at how they behave. So they've been reflected about the x-axis, right? So they grow about the x-axis like this. They're approaching y is equal to 0. sorry, x is equal to 0, the horizontal and the vertical asymptotes, they're approaching it but not intersecting, and they're approaching it upward towards infinity, versus when we have log base 3, log base 3 and log base 10. When I have values for the base that are bigger than, and we've done this before, right? We've talked about this, values of the base when they're bigger than 1, then we end up getting an increasing function from negative infinity towards positive infinity. And for y, and when we reciprocate that, when we have fractional or a base that's smaller than 1 but bigger than 0, then it's basically the reciprocated version and it's up there, right? And I want to see that they're exactly like, if you reciprocate the base, so like I want to ignore the fact that it's like, oh, less than 1 but bigger than 0. No, just look at the fact that this base over here is 3 for the blue one, and this one is 1/3, and they're exactly reciprocated versions of one another. Look at this red one over here versus this blue function, right? So they're exactly reciprocals of one another. And another thing to keep in mind is when they go through their points over here, for instance, this, when it intersects, when it has the point 3 and 1, for the blue one, right, which is the one that we just talked about, 3 and 1 happens right here. The other one, the red one, right, you can see it happens at 1/3 and 1. And so 1/3, that's 0.999. So like right over here. Oh, sorry, 0.3, sorry, no, that's 0.33333. So like right over here, somewhere in here, that's where it intersects at 1, right? You can see over here, it intersects at 1 at 0.33333. And so in that case, we understand that every time we're looking at a function, logarithmic function, this identity will always hold. And so it will always intersect at those points, right? So over here, for instance, this one will have the point 10 and 1. This one will have the point 1/3 and 1. This one will have the point 1/10 and 1. Okay, but what's important also to notice is that when I reciprocate the base, it's basically a reflection on the x-axis. Okay, so let's have a look at the questions that I've included here. How do the graphs of log base 3 of x and log base 1/3 of x compare? Well, they are reflections of one another on the x-axis. Should have left a little bit more space. I feel like I could. Let me move this a little bit. Yeah. Okay. So we're just going to say reflections of one another on the x-axis. And we've clearly observed that when we looked at the graph, right? So on the x-axis, or in the x-axis, whatever you want to say, however you want to say. And then let's have a look at this next one over here. It says the graph of y is equal to 1/bx is something of the graph of y is equal to log b x. So basically, whenever I reciprocate, then it's a reflection. They want us to write it again. So a reflection in the x-axis of the graph of y is equal to log b. So whenever I reciprocate the base, I basically just get a reflection on the x-axis, okay? So if it was going up like this, the other one would be going down like that. All right. Okay, so let's have a look at some points over here. So over here, I've included this point. We now have the two equations of the graphs y is equal to log bx reflected in the x-axis. Hence, so there are two ways that we can write a reflection in the x-axis. We can write it as log 1/bx, so I can reciprocate the base, or I can say negative log bx, right? So whenever you put a negative in front of the y, in front of the y values, you reciprocate them in the x-axis, right? You reflect them in the x-axis. So so all these positive points for the y now become the negative versions of themselves, right? Right over here. And so this was the original way where we just put a negative for the a value. And this is this new way that we've seen specifically for log, where when I reflect the base, it reflects the, when I reciprocate the base, it reflects the x-axis. Let's have a look at another exploration that I've included here with the base. So over here, look at this, look at these functions. I've included y is equal to log base 2 of x, and it looks like this. And then y is equal to log base 4 of x, looks like this. And y is equal to log base 8 of x, looks like this. Okay, so different functions, and they look pretty much the same behavior, just one is a little bit more stretched, one is a little bit more condensed, and so on. And you can see that again, because they're logarithmic functions, they intersect at 1 and 0. That's like the basic intersection always. Now let's have a look at what's going on here. If we look at the values we can see that it's being stretched and compressed accordingly, right? So then this is the conclusion we can make anytime we have bases that are multiples of, that are powers of one another. Look at this. The transformation which maps y is equal to log base b of x to y is equal to log base, now you can't really see this, so I'm going to make it a little bit bigger. Let's include the highlight with it, so resize. All right, let's make this a little bit bigger so you can see it. So when I have this exponent n over here, then on the base, right, then we have a vertical stretch about the x-axis by a factor of 1 over n, okay? And so log base b to the power of n x is equal to the same thing as doing 1 over n log b x, right? So it's basically the same thing as doing a vertical stretch, where we talked about this with transformations. It's just the a value over here would have been 1 over 1 over n if I'm doing a vertical stretch by a factor of 1 over n. Okay, and so with logarithmic functions specifically, we can identify if the base itself is to the power of something. So for instance, if I have log base 2 of x and I raise it to the power of 2, so 2 to the power of 2 is 4, then I've done a stretch by a factor of 1 over 2, right? Because I've written this as log base 2 to the power of 2 of x. And so I take this n value and I multiply all y values by 1 over 2, right? So you multiply by 1 over n, and in this case, n is 2, right? And the same thing over here, this would have been written as log base 2 to the power of 3x, and so I'd multiply all my y values by 1 over 3, okay? All right, one last topic over here, which is transformations of logarithmic functions. Typically, it will take the same form. Y is equal to a log base c, and I've changed the base to c instead of b, just so that we can we don't confuse the horizontal stretch b by the base b. And so it's okay, it's a dummy variable. I've just changed the base over here to be c, still represents the base, okay? And then b over here is my horizontal stretches, and x minus h plus k. Everything is as we've looked at it before with transformations, except in the case of logarithmic functions, there are vertical stretches that could be understood from raising the base to the power of n, and reciprocating the base could be understood as a reflection in the x-axis. Okay, but typically we'll still use the same idea with transformations, which is just using the same formula for a transformed function. Okay, all right, everyone, so that's it for graphing logarithmic functions. Join me in the example videos where we're going to look at some of these ideas in action. I'll see you there. Bye.